numbers A, B, C, D, whatever, they're bounded by something, 8,000, maybe 10,000, whatever. If they're bounded, then we know what happens at the limit of that sequence, and that irrational number. We understand that in paper, a single base, it's called. But if that sequence goes too quickly, we're in trouble. Well, how much time do I have? About 5 minutes? No, I'm learning how to count. Good. Okay, so, well, maybe, yeah, maybe, well, let me just show you that. I mean, I was measuring those, and I was saying this antenna was bigger than that here. That here was bigger than that here. You know, how do we actually measure the size of these spokes of these ears? Well, it turns out that's a job for complex analysis. It turns out there's what we call an external Riemann map that takes the exterior of the closed uniqueness, this region up here, to the exterior of the Mandelpinsky set. And we can write down explicitly what this very interesting function is. What it does is it takes these straight rays to certain curves that sometimes limit on the Mandelpinsky set. For example, this curve, 1/3 is mapped what I'll call gamma 1/3. That's the external ray of angle 1/3. 0 is mapped actually to the positive real axis, the external ray of angle 0. Okay. So, here's how we measure the size of these spokes or balls or whatever. Suppose you have a fraction, P over Q, that's periodic of period K under doubling mod 1. Okay, so what do I mean by doubling mod 1? Well, let's take 1/3. Double that, you get 2/3. Double that, you get 4/3 of mod 1, that's 1/3. 1/3 after 2 iterations, doubles back. It's up period 2 under doubling mod 1. Take 1/7, doubles to 2/7, doubles to 4/7, doubles to 8/7, but that's 1/7, period 3. Etc. 1/5 goes to 2/5, doubles to 4/5, doubles to 8/5, that's 3/5, doubles to 1/5. That's period 4. If you have a fraction that's periodic under doubling mod 1, then in fact the external ray, okay, the image of that P over Q ray in the Mandelpinsky limits at what we call the root point of a period K bulb in the Mandelpinsky. For example, if you take a 1/3 or 2/3 rays under this Riemann map, they map to a curve that limits on the root point of, these are period 2 under doubling, that would be the root point of the period 2 bulb. They limit right there. So that's the period 2 bulb. So how do we measure the size of the period 2 bulb? Well, any straight ray between 1/3 and 2/3 has to be mapped to some ray that is either landing or accumulating in here. So what we do is, if, well, that's what I'm saying, if theta is a number between 1/3 and 2/3, its external ray is stuck in there, it's homomorphic, it can't cross those rays. So, we measure the size of the period 2 bulb by the length of the number of rays that sit between 1/3 and 2/3 bulb. So the size of the period 2 bulb is 1/3. And now we saw 1/7 to 2/7. Under doubling, they had period 3. 1/7 and 2/7 is somewhere between 0 and 1/3. So there must be a period 3 bulb in here. That's the landing point. The root point is the landing point of those rays. But we've seen one right there. Yes, the 1/7 and 2/7 bulbs land there. Okay, and now the size of this bulb, the difference between 2/7 and 1/7 is just 1/7. The size of this bulb is 1/7. Whereas the size of this bulb is 1/3, much smaller. That's how we measure the size of these bulbs. Okay, if you take the 5/7 and 6/7 rays, they're down here. They also land on the period 3 bulb. The 3/7 and 4/7 rays don't land on the bulb. They actually land on that little set there. If I would magnify that, you'd see a baby Mandelpinsky. If I go to the 1/15, and 2/15 under doubling, half period 4, 1/15 goes to 2/15, goes to 4/15, goes to 16/15, that's 1/15. 1/15 to 2/15, so smaller than 1/7. So there's got to be a period 4 bulb in there someplace. Yeah, we saw it. There it is. And the size of this bulb is the difference between 2/15 and 1/15. Again, smaller. So that's how we measure the size of these bulbs. Okay, now 3/15 and 4/15, also period 4. And to check 3/15 and 4/15 is somewhere between 1/7 and 2/7. So there's got to be a period 4 bulb in there. Notice now we know the arrangement of these rational numbers, so they're telling us the arrangement of these bulbs in the Mandelbrot set. Someplace in there, there's going to be a period 4 bulb. Let's zoom in on that. Turns out it can't be a bulb attached to the period 3 bulb. Their periods are all multiples of 3. The biggest thing out there is a little baby Mandelbrot set, and yeah, that is period 4 in the entire group. So understanding the arrangement of rational numbers, which most of us do, they're periodic, undergoing, tells us the arrangement of all these bulbs in the Mandelbrot set. Again, kind of a fascinating connection with number theory. Okay, so what do we know about the Mandelbrot set? Well, we know that if you give me any rational external ray, they land at a single point in the Mandelbrot set, not just on those that are periodic on the other. All those rational external rays land at a single point. The ones that are periodic on the doubling land at root points. Ones that are non-periodic land at other points. Sometimes they're what we call Mishevich points. They're the junction points of these spokes, of the endpoints. That's how we measure the lengths of these antennas. Okay? And then the highly irrational rays also land at points. You understand what goes on there? I told you what highly irrational meant. Okay, but what do we not know about the Mandelbrot set? Well, we've got those irrationals that are close to rationals. We don't know if those rays land. Remember those bulbs, they get more and more intricate, more and more spokes as you get closer and closer to those irrational points. The geometry is getting very intricate. Maybe those rays come in and start moving like crazy and accumulate on something. We don't know if those rays are landing. So we won't understand quadratic functions until we figure that out. So that's the MLC conjecture, local connectivity conjecture. The boundary of the Mandelbrot set is locally connected. We can prove that it's topologically locally connected, and it's a fact that all these rays land. Okay, if they all land, we finally understand x squared plus c. But we don't know that yet. And if they don't all land, we're in real trouble. We'll never understand x squared plus c. The end of mathematics. You don't understand x squared plus c. If you walk up to a physicist and go, oh boy, we just get out of it. Yeah, you can see these pictures are getting more and more intricate. Well, let's see. I wanted to show you one more thing. If I have one more second. I'd just like to go to my research. I think one of my most important contributions is another sequence. A sequence that I think is going to be more important than the Fibonacci sequence as we go on. Okay, here's another sequence that I think is incredibly important. Okay, let me just take the denominators here, not the numerators. So this is 0 over 1 bulb, that's 1 over 2 bulb. The largest bulb between the 1 and 2 bulb in the northern direction is this. Add those denominators, it's 3. The largest bulb between the period 1 and the period 3 bulb is the period 4 bulb. The largest bulb between 4 and 1 is 5. And 5 and 1 is 6. And 6 and 1 is 7. This is a sequence that I think is going to become more important than the Fibonacci sequence. So I've named it after myself. So if you ever happen to come across this sequence in the future, please call it by its and finally,
difficult because the nature is starting from 0, and the 1 second is starting from 1.
Oh, was that the, what sequence were you calling?
The nature of numbers starting from 0. This is the first time.
Well, that's an extension of the Devaney sequence of zero. That's another paper. Anyway, if you're interested, I actually do a lot of work with high school students and teachers, and there's some stuff on my website that allows you to, there's applets to zoom in on the handles and make movies and work handles, etc. Applets for other complex functions and all sorts of other things you may use. Any of that, maybe I should stop here. Thanks very much.
Any questions?
How do you say zoom rate? Every time I see this more zoom, we see more and more. That's when I say every deep inside is a new computer, a new one. Yes, I read. Zoom. How far can you go? What's the latest?
In terms of just the computer, or in terms of
Get the computers, get the computers.
oh, actually, I mean, I zoomed during the break into that 37,000 spoke thing. Yeah. You can zoom as far as you want. Well, the things get so intricate. You know, you got 37,000 spokes, it's kind of hard to see them in one picture. And you get 10 billion spokes, and you never going to see them in one picture. So you can only zoom so far, but you don't have to, because we know what that matters. So why zoom? Just tell what's going on.
More questions?